Okay, welcome to Investigation 8A. This investigation has to deal with global circulation, and in order for me to explain and display how global circulation works, I have to show you a simplified model of the world. So this is my simplified model right here, this image that you're looking at. It's just half the world. I cut the southern hemisphere out. Why? Because I'm Eurocentric, but sorry, southern hemispheres. But what I'm actually going to show you here actually also applies in the southern hemisphere. So in this video, I'm actually going to introduce you to two different models. And each one of these models takes a very complicated atmosphere and simplifies it so we can actually learn stuff from it. The first model I'm going to teach you is what's called the single cell model. In the single cell model, there are a few things you need to know about our Earth. Write these down. I also have these on the actual lab manual. But here they are. The first one. The Earth is not tilted. So we don't have seasons. The sun is over the equator year-round. Okay, so the sun is over the equator year-round. Number two. The Earth is uniformly covered by water. So we're getting rid of land and any of the sticky stuff that makes land what it is. That allows for land to interfere with the atmosphere. And then the third thing is, for the single cell model, there's no rotation. And hence no Coriolis Force. So we're only going to be dealing with the pressure gradient force here. Alright? Now that being said, let's begin to construct our model. So, the sun is over the equator. Therefore, the equator is going to be nice and, let me actually use orange here. The equator is going to be nice and hot. I don't know why that's not writing. Oh, here we go. Equator is going to be nice and hot. Well, what does hot air do? Hot air rises. So what we're actually going to do here, using this little brush, I'm going to indicate that over the equator, hot air is rising. Now, if you remember from the hand twist model, and by the way, this whole model is actually going to rely on stuff that we've already covered in previous investigations. If you remember from the hand twist model, air rises in low pressure. And since we have rising air here, we are going to have lots and lots of low pressure here at the equator. Alright. On the other hand, as you move away from the equator, the sun gets lower and lower and lower and lower and lower and lower on the horizon. That's true. What that means is that the North Pole, now we're the farthest away from the equator that we can be, here on Earth anyway, is going to have cold air. So up here, North Pole is going to be cold. And what does cold air do? Well, cold air sinks. Cold air sinks. And this creates a big, beautiful blue high pressure system over the North Pole. So we have rising air and low pressure at the equator, sinking air and high pressure at the poles. Now if you remember the pressure gradient force, where do winds blow? Winds blow from high to low. And so what actually happens is, here at the surface of the Earth, winds are moving from the pole down to the equator. Down to the equator. Meanwhile, higher up in the atmosphere, since we have all of this rising air up here, the area up here is going to have more air molecules, therefore it's going to have higher pressure. Meanwhile, over the pole, there's air that's sinking here, so higher up, we call this aloft, there's sinking air, therefore there's going to be less air up here. So higher up, we are going to see air traveling from the equator to the poles. And this right here is what is called the Hadley cell. the Hadley Cell. And let me label that for you. Okay, so that's our single cell model. Air rises at the equator, sinks at the pole. We have low pressure at the equator, high pressure at the pole. Take a moment. Any questions you have, I recommend writing them down and then sending them to me as an email. Okay, now let's do part 2 of this. So, in part 2, we are actually going to add some complexity to our model. So, in the single cell model, we had a, Earth uniformly covered with water, didn't rotate, had no tilt. But let's actually let rotation back into the mix. By adding rotation to our model, we've introduced the Coriolis Force. And the Coriolis Force causes wind to turn into a different direction. That actually takes the cell here and splits it up into 3 different cells. In this lab, you're actually going to construct these cells, but I can at least get you started. I will help you with the first one. So, here are a few things that are still true about this model. The warmest temperatures are still near the equator. As a result, near the equator, we still have low pressure. That doesn't change. We will still have low pressure near the equator. However, we will also still have rising air at the equator. That doesn't change. We also still have sinking air and high pressure at the poles. All right, so get my little arrow there. It's a little sloppy, but that's okay. Here's what's different, though. This air that rises at the equator isn't actually going to make it all the way to the pole. Instead, what's going to happen, due to the Coriolis Force, as it begins to make its journey towards the pole, it's actually going to begin to sink back down to the ground at about 30 degrees, both north and south, but right now we're just focusing on the northern hemisphere. And so we actually end up getting sinking air at 30 degrees. Recall from the hand twist model, which type of pressure system was air sinking in? That's going to be the kind of pressure you have at 30 degrees. That's going to be the kind of pressure you have at 30 degrees. And then finally, once this air sinks back down to the surface, it begins to move its way back to the equator. The next thing I'll say is that you're going to see 2 more cells. You're going to see another cell that starts with sinking air at 30 and ends with rising air at 60. And then another cell that begins with rising air at 60 and sinking at 90. I'm not going to draw the cells for you because I want you to get a little more comfortable with this, but hopefully this first cell, and the name of this cell is also called the Hadley Cell. This cell here is called the Ferrel Cell. This cell here is called the Polar Cell. But I want you to be a little bit more comfortable with drawing them and then figuring out what kind of pressures are present. Since we have sinking air at 30, we should have a type of pressure. Hint, what kind of pressure does air sink in? At 60, we have rising air. Hint, what kind of pressure do you have rising air in? And that should be all that you need to know for the single cell and the 3-celled models, at least for the time being. What I'm going to do next is I'm going to show you a little bit about the windy.com website. And then after that, what I'm going to do is I'm going to then introduce you to what are called the trade winds.